All right, guys, we will finish this lecture. Okay, so we talked about roughages, the importance of roughages, how they stimulate chewing, which stimulates saliva production, which stimulates buffering of the of ruminal fluid. That should become even clearer how important it is after we go through all the ruminant dysfunction uh, in the lecture I should be giving today, but we got to catch up. Okay, so chewing roughages is important. However, the degree to which roughages are processed impacts how much they will stimulate chewing. Okay. So they've proposed this physically effective neutral detergent fiber or PENDF, which uses the Penn State particle size separator to basically measure particle size distribution of your ration. Okay. And we can watch this YouTube video after we buy our Liberty Mutual insurance. Okay. So Penn State Extension, really this was started for dairy, but it has some application in finishing diets.
To determine the particle size of gorges and TMRs. It's a popular tool because it's easy to use in the field or at the feed bunk, and it produces repeatable results from as-fed samples in just a few minutes. Dr. Judd Heinrichs and his graduate students developed this tool and have continued to improve it as our understanding of how particle size influences the health and production of dairy cows has changed. In this video, Dr. Heinrichs will tell you more about the Penn State particle separator and how to use it.
This is the Penn State particle separator. It's designed very much similar to the ANSC separator.
Whatever that is.
It has screens that are 90 millimeters, 7 millimeters, 4 millimeters to give us effective fiber, and about a hand. And one of the unique features about this is that the thickness of the screens are proportional to the diameter of the holes. That's what makes it work. There's also available a screen which is 1.1 millimeters. That's actually going to determine the average size of leaving the rumen of a cow. Some people may use that fine particle.
Okay, add feed to the top. We did a project in Bushland where we had to do this on like weekly samples or something and 3 different diets. It ends up being quite the workout, but
Weight and on our website.
yep. So you weigh the weight of the feed that accumulates on each screen, and then you express that as a proportion of the total weight. It tells you what percent of the diet is greater than 4 millimeters, or what percent of the diet is less than 8, or whatever. So the US, we use 4 millimeters as our smallest screen to indicate particle size uh, for PENDF. So anything that's 4 millimeters or greater, we would consider as contributing to physically effective NDF. So you multiply that fraction of the feed by your NDF content of the diet, to estimate PE/NDF. Canada uses some other number, and so it's not consistent between Canadian data and US data. So I tried to do a meta-analysis to look at how physically effective NDF impacts like feed intake, rumination behavior, and things like that. And it was very frustrating that they weren't very consistent, but it is what it is. Okay. So theory is larger particles will require more mastication, so more chewing will stimulate chewing, produce more saliva, and produce more saliva buffering. Okay. Most or all forages that are fed in finishing diets are going to be processed. Okay. So there we have a picture of ground corn stalks, ground alfalfa hay, ground prairie hay. For silages, they will be ground or chopped before they go into the ensiling process or into the silage pit. Other dry forages will be typically ground as round bales, okay, using tub grinders. And I don't know. Let's try this one. Valley Vet.
This land to my great grandfather. The colts we raised.
So this is a hay buster, the big bite tub grinder. So there are flails at the bottom of this grinder, and then at the bottom of the flails are different screen sizes. So you can grind them to different lengths. Then this has a conveyor belt that shoots the ground hay. Typically, you would put it in a commodity barn as you grind it.
Five design enhancements and features to our products that you tell us make the most sense to the.
Okay, guys get the idea on that? Now, a lot of people will contract 135.
No, we didn't eat that much, so we ended up
So you have people that have contractors where they'll literally have these tub grinders on the back of a trailer that's hauled by a semi truck. It'll put out stabilizing arms, and then it'll have an what the hell is that thing? Or heck, what the heck is that thing called? That arm, grab the bale, put it in the tub grinder, and they'll grind God knows how many bales of hay a day, right? So you can contract these people to come in, grind a bulk of your hay at a time. That's what larger feed yards will do if they're feeding dry hay.
Chews it up and then puts it out the conveyor into that big pile.
Get the idea? Okay. All right. Typically, they're being ground to 7.6 centimeters in chop length. Okay. So this experiment looked at cattle that were fed 16% roughage or 8% roughage. And then, so it was a 2x2 factorial. So they had 2 roughage inclusion levels and then 2 chop lengths. So 2.5 centimeters long or 7.6 centimeters long. Okay. Based off of the liver abscess incidence, right? Going from a 7.6 centimeter chop length to a 2.5 centimeter chop length, independent of roughage inclusion, okay, having that really small particle size cause more liver abscesses, right? So you can assume that it's stimulating less chewing. There's lower ruminal pH that are leading to those liver abscesses. Okay. An important consideration is that byproducts that can be considered roughages can have an appreciable amount of PE/NDF. Okay. So this was a paper, Andrea Warner published this when she was doing her PhD. They looked at prairie hay, sweet bran, whole cotton seed, and then cotton gin trash or cotton burrs. Okay. So these are the different ingredients. Prairie hay was 66% NDF, sweet bran, whole cottonseed, and then cotton gin trash. You can see the NDF content there. Here's where they measured the particle size of those using the Penn State particle size separator of each of these specific ingredients. Prairie hay was obviously had particles that were had more particles that were greater than 4 millimeters in length. However, a lot of these also had particle sizes that were greater than 4 millimeters, so that your estimated PENDF of prairie hay was higher than these other ingredients, but these are still appreciably high, right? So that if you are bringing in, if you're replacing some corn with a byproduct feed, it's a little safer because you're replacing starch with some physically effective NDF, even though the actual particle size of those ingredients could be relatively small, and NDF content is less than whatever roughage you're using. Okay, here's another study, looked at the same thing. This is steam flake corn. As you'd imagine, the PENDF of steam flake corn is very limited. Wet corn gluten feed, so this would be sweet bran, a little higher. This is short grind corn stalks, and this would be a longer grind corn stalks. So a shorter grind is going to have less PENDF than a longer grind. Okay. That was done by Wes Gentry out at Bushland when he was doing his PhD out there with Jenny Jennings. Okay, so Warner looked at formulating a ration that they were fed a common receiving diet. Okay, they had a control where prairie hay was used as the main roughage source. Okay, they compared that to a diet that was formulated to have similar physically effective fiber, but it contained no prairie hay, and only the roughage source was only cotton gin trash, so cotton burrs or whole cottonseed. Okay, see, they got a similar physically effective NDF, but the source of that physically effective NDF was either all cotton byproducts or all hay. Okay. They saw no real difference in average daily gain, maybe a tendency for the cotton byproduct diet to have a higher average daily gain over the whole feeding period. Okay. The cotton byproduct animals ate a little bit more. I think that should make sense because they were consuming a diet that was composed of smaller particles. So it should have a faster rate of passage. So they'd be able to eat a little bit more. And that resulted in no real change in gain to feed. Little bit of an increase in average daily gain, but a little bit of increase by dry matter intake, so that feed efficiency was not different. Okay. Then this shows liver scores, which we can use as like a proxy of ruminal pH, because as you'll see in our today's lecture, ruminal pH is going to drive liver abscesses. Okay. They saw no difference in prevalence of liver abscesses from these cattle. Make sense? Cool. Now let's switch to today's lecture. If you guys showed up late, here's the code for the quiz. Okay. All right. So, I want you guys to know the etiology of subacute and acute ruminal acidosis. Okay. Understand how ruminal acidosis is really the root cause of most of the disorders that we see in a feedlot. Okay. So, understand how it can lead to laminitis, ruminitis, parakeratosis, and liver abscesses. Okay. Know the difference between a free gas and a frothy bloat. Okay. Most bloat is caused by frothy bloat. Okay. Know how legumes and cool season annuals can lead to frothy bloat in grazing cattle. Okay. Understand how low ruminal pH can lead to frothy bloat in feedlot cattle. Be able to describe how low PE-NDF can lead to frothy bloat. Okay, and then be able to distinguish between nitrate and prussic acid poisoning. Okay, they have a similar effect on the animal, but the underlying mechanisms that cause that effect are different. So in essence, I want you to be able to compare and contrast those two disorders. Okay. This paper was published out of Canada. They looked at, they kind of did a review of the literature on ruminal acidosis and low ruminal pH. Okay. So if we have a period of increased intake, so if those animals go to the bunk and they gorge, okay, and that diet is composed of rapidly fermentable carbohydrates, so high starch, high ruminal available starch, it's going to cause an increase of acid production, so our volatile fatty acids, but also lactate or lactic acid. So this is going to drive down ruminal pH, and under normal circumstances, that animal's normal physiology should be able to clear volatile fatty acids out of the rumen at an appreciable level to maintain pH in the rumen. Okay? However, if blood pH begins to decrease as a result of those acids being absorbed from the rumen wall, so if blood pH starts decreasing, that animal will stop having rumen motility. Okay? It'll stop absorbing these acids because it's trying to protect the overall health of the animal, right? If blood pH drops too low, then you can get metabolic acidosis and lead to death. Okay? So, blood pH starts to decrease, animals' responses to decreased rumen motility. So that's the normal cycling or the contractions of the rumen. Okay? It's going to decrease VFA absorption across the rumen wall. It's doing this again to protect against metabolic acidosis. Okay? So, acidosis can be defined in many ways. This class will use subacute acidosis and acute acidosis. Okay? One thing I want you guys to understand is that ruminal acidosis is really caused by a vicious cycle. Okay? So, animal consumes feed. We have increased growth rate of bacteria. It's going to increase VFA production. That VFA production is going to suppress ruminal pH. Okay? As ruminal pH starts to go down, bacteria that can tolerate those low pH levels are going to further exacerbate the problem. Okay? You're going to have an increase in strep bovis, which is going to produce more lactic acid. Lactic acid has a much lower pH cause or pKa than the other volatile fatty acids. Okay? So if lactic acid production outpaces the ability of lactic acid utilizers in the rumen, going to further suppress rumen pH. If it gets below a pH of 5.0, lactic acid utilizers can't tolerate that really low pH. Okay? So you have lactobacillus species proliferate. They're further going to produce lactic acid, further going to suppress the ruminal pH. That really low rumen pH is going to stop normal motility, cause ruminal stasis. So it's further going to accumulate acids in the rumen. Okay? Such to a point that this ruminal stasis will not be able to prevent metabolic acidosis, which is decreases in blood pH, and that metabolic acidosis will lead to death really fast. Okay? So it's a vicious cycle. Any questions on that? Cool. So subacute ruminal acidosis is repeated occurring prolonged periods where ruminal pH decreases between 5.6 to 5.2. Okay? The low rumen pH is caused by excessive accumulation of volatile fatty acids without persistent lactic acid accumulation. Okay, so pH has not dropped enough for lactic acid to start really accumulating to drive acute ruminal acidosis. Okay. So typically in subacute ruminal acidosis, the animal's own physiological response will ameliorate that bout of low ruminal pH. Okay. For acute ruminal acidosis, we have a severe drop in pH, so somewhere 5.0 to 5.2. Really low pH, only lactic acid producing bacterial function, so that's further going to drive down ruminal pH, so causing that vicious cycle. That animal's normal physiological responses will not stop this process, so it needs almost immediate intervention. Okay. Only real options to intervene on this process, you could try to drench with buffers. That's oftentimes not going to be adequate. So the only real option is to pump out all the rumen fluid that you can and then replace it with a healthy animal's rumen fluid. So do you think many feedlots will do that or will even find this issue in time? No. So typically in a commercial feedlot, if they get to acute ruminal acidosis, that animal's going to die. Okay. Eventually, rumen pH drops so low that even the ruminal stasis will not protect the blood metabolic pH from decreasing to a low enough degree that metabolic acidosis will lead to death. Okay. Yes.
I can't what it is, but like a lot of them are going to the liver, correct?
Yeah, so pretty much liver gets first choice, right? Well, take that back. Rumen epithelium get first choice. Okay, their predominant VFA of choice is going to be butyrate. So we'll talk about how that's important on some of these other disorders. After that, so 90% of butyrate is going to be utilized by the ruminal epithelium. The rest of that, first choice is going to go to the liver. Most propionate is going to be consumed by the liver. However, the majority of acetate is going to go to the skeletal muscle. But yeah, that portal drain, I don't even remember the name of the hepatic. Yeah, takes it right from the rumen to the liver. Yep. But a lot of that acetate will actually go to adipocytes, skeletal muscle, that type of thing. Yep. Good question. Okay. All right. Subacute acidosis, also called subclinical acidosis. So ruminal pH is suppressed by a slug intake, so a fast intake of rapidly fermentable carbohydrates into the rumen. So a ruminal pH of below 5.6 has been suggested as this threshold. Clinical signs are difficult to observe or detect. Okay, there's probably some low level of subacute acidosis happening to every animal consuming a finishing diet. Okay. However, we can use different signs, some different signs, such as animals that are experiencing these bouts of subacute ruminal acidosis will have erratic feed intake behavior, and that erratic feed intake is going to suppress performance. So that's one sign. However, another sign is loose stools. Okay, so if we have a manure score of 1, that's a big indication of low ruminal pH or subacute ruminal acidosis. Okay, so the reason subacute ruminal acidosis leads to loose stools, okay, runny manure, is ruminal acidosis accumulation leads to ruminal acid accumulation leads to greater ruminal osmotic pressure. That osmotic pressure in the rumen is greater than what's in the blood. And so when that happens, it's going to draw water from the animal into the rumen. So that physiological response is trying to dilute that acid to bring that pH back up. Okay? Increased water in the gastrointestinal tract makes for these animals to have diarrhea, right? Okay, so net influx of water into the rumen from the blood will cause dehydration to cattle. More water in your stool, looser stool, lower manure scores. And then, so we use these manure scores as an indication of low ruminal pH. So if you remember, that's one of the signs that your feed caller or bunk reader is going to use when they're deciding if they want to bump animals. Okay, that's one of the animal signs. So if animals are having lower fecal scores, maybe they're going to be more conservative in their feed calls. Okay. All right, this same paper out of Canada made this graph, which is really kind of cool. So the solid black line is ruminal pH. This range is the day. So day 1, day 2, day 3, day 4. And then 9.5, 8.3, 3.7, that's the amount of intake that animal had during that day. Okay? So day 1, animal eats 9.5 pounds. You can see ruminal pH goes below this 5.8 threshold, spends an appreciable amount of time under that threshold. Day 2, intake decreases just a little bit, but it's still at 8.3 kilograms per day. We see further suppression of pH, a further duration of time spent below that 5.8 threshold. Okay? This low rumen pH causes them to feel sick, have some malaise, so that day 3, they barely eat anything. They went from eating 9 to 8 to just under 4 kilograms per day. Okay? Because they ate little, their rumen pH stays high. Day 4, they eat a little bit more, so they're starting to feel a little bit better, but not as much as what they were eating. Ruminal pH stays high. Day 5, they start eating some more. Okay? Ruminal pH starts to dip again below 5.8. Next day, they eat 8.5. Ruminal pH starts to dip below 5.8. The next day, day 7, again, they're back to where they were almost eating on day 1, and that's causing ruminal pH to drop again. Okay? So if we were to project that out, we would see this cycle where these animals are having gorge, low rumen pH, feeling malaise, and then not eating as much. So it's causing this erratic intake pattern. Does that make sense? Okay. Okay. Gorge, malaise, off-feed cycles is what I like to call it. Okay. I think I said all that. Okay. So acute acidosis, also called clinical acidosis, at very low pH, so less than 5.2, lactobacillus, so these lactic acid producing bacteria really proliferate. Other bacteria can't really function. So it allows that lactobacillus bacteria to fill that niche that's being vacated by those other bacteria that can't tolerate low pHs. Okay? They're more tolerant to low pH, produce more lactic acid, causes that vicious cycle. The lactic acid production is greater than lactic acid utilization because these lactic acid utilizers like Megasphaera eldenici or elsdeni, whatever, can't function at those low rumen pHs. So it creates that vicious cycle where more lactic acid further drives down rumen pH, which produces more lactic acid, which further brings down rumen pH. Okay? So eventually there will become a point of no return where rumen pH drops so low, okay, and these other bacteria can't function so that the onset of acute acidosis or clinical acidosis can't be reversed. Okay? Okay. Rumen pH can't be modulated. That acids will be absorbed into the bloodstream even with low rumen motility. And if it outpaces bicarbonate's buffering capacity in the blood, you'll get metabolic acidosis, and that will lead to death pretty shortly. Okay? So, prevention of acidosis. Appropriately transitioning animals to finishing diets. Okay? Providing adequate PENDF so that to stimulate that chewing and saliva buffering. Okay? Like we talked about in the last lecture. Bunk management, so adequate and appropriate feed calls that you're not trying to push animals too hard. You're trying to avoid those gorge, malaise, off-feed cycles. Okay. We can feed buffers, so we can feed bicarbonate. Okay. Urea actually has a little bit of a buffering capacity. As urea gets converted to ammonia, it takes up some hydrogen, right? And then feeding ionophores. Okay. So monensin can help prevent some ruminal acidosis. One, it's going to suppress intake by a little bit. Two, it's going to help stabilize day-to-day intake and prevent those gorge cycles. Okay. So now we're going to talk about all these different disorders that kind of stem from subacute ruminal acidosis. Okay. Laminitis or founder. Okay. So low ruminal pH causes an accumulation of acids in the rumen, which cause cell lysis, and that also causes damage to the ruminal cell wall, okay, the epithelium in the rumen. We'll talk about that more. Okay. Damaged ruminal wall decreases epithelial barrier function. Death to cell lysis, so death to cells, cause production of endotoxins like lipopolysaccharides or LPS. So you have more transmission of this LPS across the rumen wall into the bloodstream. And then it's been suggested that endotoxins will weaken the laminae in the hoof, okay? Leads to laminitis. So in a healthy hoof, the laminae is the cushion between the hoof wall and the bone that's coming down from the tip of the hoof. So that is right here, this cushion right here. So this is the laminae. So LPS causing that to break down will make, so the laminae, healthy laminae, is going to hold that hoof bone parallel to the hoof wall. So by weakening that laminae, this coffin bone right here will push downward, and it'll cause that, or excuse me, this coffin joint will push downward, cause this coffin bone to protrude out, and putting pressure on the sole. Okay. You can have varying degrees of this laminitis. So you'll see some animals that it's so bad that they're literally walking on their heels, and their toes, the toes of that hoof will be pushed up. Could also just be what's called hook foot or hook hoof, okay, where those hooves kind of form this hook, right? They look like pinchers, like a crab almost. You see this a lot in feedlots. When it gets this bad, you'll start seeing some real issues with lameness. Okay. So once laminitis is set in, there's no real treatment. It's not reversible. So animals that get this bad, become foundered or achieve this level of laminitis, will always have walking issues. Okay. All right. So low rumen pH causes ruminitis. Okay. Ruminitis is inflammation of the rumen epithelium. So you can see this reddening here in this picture. Doesn't really show up too well on the screen. But this inflammation will cause the epithelial cells, that ruminal papillae, to literally shed off of the rumen wall. Okay. This is pretty painful. And so that's part of the reason why that inflammation on the ruminal wall is part of the reason why animals will stop eating, because their rumen just feels hurt. Okay. So ruminal papillae slough off of the rumen wall. They will be able to detach real easily, and once they're gone, they're not going to grow back. Okay. Once this rumen wall starts to heal, it will scar over, and no more epithelia or papillae will grow on that part of the rumen wall. So if we have lower papillae, what will that lead to? Less absorption of VFAs. So we will see animals have reduced performance for the rest of the time that they're on feed, okay? Because a lower amount of VFAs can be absorbed from the rumen. And then, yeah, unlikely for them to recover that lost absorptive capacity. Yeah, I think so. I don't know if that's ever necessarily been like proven, but you end up with these animals that are kind of problem childs, right? They're more prone to experience these, and I think that could be a good explanation. Okay, so ruminitis, this damage to the rumen wall is part of what's going to increase or decrease barrier function. So it's going to transport more LPS across the rumen wall. Bacteria will actually translocate across the rumen wall, and we'll talk about that more with liver abscesses. Okay, parakeratosis. Okay, this is another issue that can cause uh, translocation or barrier function issues with the rumen wall. Okay, we get a hardening and enlargement of the papillae in the rumen. Okay, so if you have a period of time where that papillae is more exposed to a higher concentration of these VFAs, it's going to hypergrow. Okay, because especially butyrate, is what is going to provide the energy for the rumen epithelium to produce new papillae. Okay, so if they have more acid that's physically around those rumen papillae, it's going to increase growth. Okay, so you'll see that several papillae may grow together. They'll become very hard, very keratinized. Okay, that hardening will create these like grooves between them, which can cause lesions and parakeratosis and translocation of bacteria across the rumen wall. Okay. Um, yeah. So these will end up growing together, enlarge, harden due to excessive layers of keratinization. They become excessively nucleated, squamous epithelial cells. And so that's the main histological difference that you see. So whenever I say histological, that's what these are. They're looking at rumen papillae and their structure using histology, and they're basically staining cells, okay, so that they can look at it under a microscope. Okay, so this is a papillae from a healthy animal consuming a high forage diet. This is a papillae from an animal that's consuming a high concentrate diet. Okay, so you can see the detachment of the outside of the papillae from this inside part of the papillae. These black dots are nuclei. They become hypernucleated. Okay. So sloughing of the stratum corneum and demarcation of cells through the epithelial layers. So this keratinization causes that hardening. You get cells or papillae that grow together and form these clumps. These clumps, which are hard, can cause lesions, and those lesions can cause open wounds. Open wounds decrease barrier function of the rumen, decrease barrier function of the rumen, increase translocation of bacteria and LPS across the rumen wall to cause further problems. Does that make sense? Any questions on this? Okay. Also, these papillae are going to be less effective at absorbing nutrients. So it's going to decrease ruminal absorption capacity, which can hinder performance. Okay. We've talked about translocation and barrier function of the rumen. Obviously, if we get bacteria that translocate from the rumen into the bloodstream, it can cause some issues, right? Okay. Damage to the rumen epithelium from ruminitis or parakeratosis increases the potential for microbes to translocate out of the rumen into the bloodstream. Once they go into the bloodstream, they will go to the liver. Okay. I will, just like this says, new evidence out of England is also pointing to hindgut So the cecum as being a substantial place where translocation of bacteria and subsequent ruminal or liver abscesses can form. But the primary theory is acidosis causes ruminitis, or parakeratosis causes bacteria to enter the blood portal blood and then to migrate to the liver and cause these abscesses. Okay. Predominant bacteria is Fusobacterium necrophorum. Okay. It is predominant because it is an obligate anaerobe. So what does an obligate anaerobe mean? So that would be a true anaerobic bacteria. What would obligate indicate? It can function in aerobic conditions. So that's why Fusobacterium necrophorum can enter the bloodstream, which has oxygen, and still survive and cause issues when it reaches the liver. Okay. So this has been long established as being the main culprit of liver abscesses, but that's been through traditional microbiology, where they're actually like streaking these abscesses onto plates and culturing these bacteria. These are more easily cultured than other bacteria, like Salmonella, which could be a contributor to liver abscesses. They're easier to culture because they are obligate anaerobes. Make sense? It's hard to keep that traditional microbiology, that plate where you're trying to culture these bacteria, it's hard to keep them anaerobic. So it's easier to culture obligate anaerobes than it is true anaerobes. However, they have looked at some gene amplicon sequencing. So using modern techniques, they have isolated or found Salmonella in some liver abscesses. But this study, Herrick, in 2022, looked at over 130,000 livers from 7 packing plants. They cultured 193 of them. They found Fusobacteria was present in 80% of the liver abscesses, and Salmonella enterica was present in just under 28%. So Salmonella is probably contributing some to liver abscesses, but the big driver is this Fusobacterium necrophorum. Okay. Liver abscesses. So as liver abscess scores increase, feed intake is going to decrease. Average daily gain is going to decrease. Feed efficiency becomes poorer. Okay. Think about animals that have higher incidence of liver abscesses are probably also experiencing more subacute ruminal acidosis. They're also probably experiencing more parakeratosis, probably also experiencing more ruminitis. And all these, ruminitis and parakeratosis reducing absorptive capacity is probably also suppressing their ability to convert feed into energy, because it's reducing absorptive capacity out of the rumen. Okay. So meta-analysis, they looked at a couple of different papers here. So 0 would be a liver without any liver abscesses. A minus, going from A minus to A plus, increases the severity of those liver abscesses. And pretty much as you increase severity of liver abscess, live weight at harvest starts to decrease. Hot carcass weight will decrease. And then this trim due to abscesses, so what percent of the carcass they had to trim is going to increase. So why would we trim livers? Or why would liver abscesses cause us to have more carcass trimming? What do I mean by carcass trimming? What's that? Well, okay, so if we harvest an animal at the slaughter packing plant, okay, they have that hot carcass, okay. Animals with more severe liver abscesses they will have to trim more of that carcass off for some reasons. One could be a liver abscess bursts, ruptures onto part of the carcass, and they need to do it for meat safety purposes. Okay. Another, when you get to A plus, they call this A plus adhesions, and these livers will actually adhere to the diaphragm, which is the skirt steak. All right. And so if that liver, that condemned liver adheres to the skirt steak, they'll have to remove it from the carcass. So severe liver abscesses that are inedible, you have the cost of that liver that you can't sell. We don't eat liver really in the US, but some people do in other countries. Okay. You also have any cost of carcass material that you have to trim off, such as the skirt steak from a liver that's adhered to the diaphragm. That makes sense? Okay. Because of that excess trim, you see that dressing percent will decrease as liver score severity increases. Okay. You have more carcass that needs trimmed. So you have lighter hot carcass weights. Lighter hot carcass weights relative to live weight is going to decrease your dressing percent. Everybody follow? Any questions on that? Don't look so thrilled. Okay. And this is kind of what I just said. All right, so liver abscesses are related to a lot of different things that can impact the profitability from that animal. We see lower feed intake, likely due to subacute ruminal acidosis and feel that gorge, malaise, off-feed cycle, and erratic feed intake behavior. Average daily gain decreases. They're eating less, so they're unable to convert as much feed. Also, they have lower feed efficiency because lower absorptive capacity of the rumen. Okay. A plus adhesion has poor impact or a significant impact on carcass weight and dressing percent. This is because of poor performance yielding lighter body weights, but also because they have more trim due to abscesses being increased in the liver. So you have trim due to liver adhesion to the diaphragm, which is the skirt steak, like I just said, then liver abscesses that literally rupture and cause contamination to the carcass. Okay. All right. Incidence of liver abscesses have increased. In 2011, it was 13.7%. In 2016, it was around 18%. The value of the cost is estimated to be somewhere between $20 to $80 per carcass, depending on the severity of the liver abscess and how much carcass trim they have. Okay, this estimated cost is not going to be related to any lost performance, right? So that's not capturing that. This is just due to loss of selling an edible liver and then carcass trimming. Okay. This same paper, 2022, again, they collected over 130,000 livers, and they collected them from 7 different beef processing facilities. Okay. Dairy type animals have greater incidence of liver abscesses than beef types. Why might that be? On feed longer is probably the main driver. Also, they just like to chew on a lot more things. So they literally will cause damage to their mouth. Probably have some bacteria that translocates from that. Then also they will are more likely to get hardware disease, which I think I have a slide on hardware disease coming up. Got 20 minutes? Okay. Because they're more likely to just eat metal that they find. They're just more playful, I guess, or get more bored. I don't know. Okay. So I don't know of any data that has looked at within beef animals the incidence of liver abscess from those that were backgrounded in a feedlot versus backgrounded on pasture. But that would be interesting to look at. A conservative estimate from this paper is that within the entire U.S. beef industry, liver abscesses cost somewhere around $60 million. But that is from direct cost of the carcass, and it is not related to any lost performance, right? So of that, liver losses was the bulk of it, so 41.6 million annually. Viscera loss on average was $2 per head. Relatively low cost per head, right? And the organ viscera, the offal, right? We don't eat offal, but again, other foreign countries will. Okay, that's a low per head, but uh, cost. But you multiply that by a large number of animals that get finished, and it ends up being a large amount of money. Does that make sense? Okay. Okay. People have looked at developing a vaccine against liver abscesses, and it was effective, and it was approved by the FDA. But because it's a low cost per head, it was never really adopted in the industry. Okay. And I've already said this. All right. Prevention. So, same strategies to prevent ruminal acidosis. So, feeding adequate physically effective fiber, using ruminal buffers. Likely ionophores are going to have some benefit to liver abscesses because it's going to stabilize intake. And then good bunk management. Okay. It's also pretty common in the southern plains to feed Tylen. Okay. Tylen is a antibiotic. Okay. It's a macrolide antibiotic, so similar classes like Micotil or Draxin. Okay. They're feeding it at subtherapeutic levels. So they're not feeding this Tylen to treat any illness or even at a large enough dose to treat illness. They're providing it at subtherapeutic levels to, I don't know. I don't know if we really even know how feeding Tylosin will reduce the incidence of liver abscesses. Okay. But since this macrolide antibiotic is of human importance, okay, it requires a VFD, so veterinary feed directive. Okay, so Tylosin phosphate here, this Tylen 100 is labeled to be fed at 60 to 90 milligrams of Tylosin per head per day. It's been shown to reduce the incidence of liver abscesses somewhere around 40 to 70%. So it has a substantial impact, a substantial reduction in liver abscesses. This paper by Alyssa Word, published in 2024, she runs the science there at Cactus Feeders. So pretty much oversees the research that's going on at Wrangler Feed Yard in Tulia. Conducted a study, showed that Tylosin reduced incidence of liver abscess by 32%. So they took liver abscess incidence from 19% of animals down to 13%. Yep.
Program developed, like a third-party program, have vaccines or your cattle don't have liver abscesses come into play at some point?
No. And the incidence of liver abscesses, my suspicion is they're increasing. They're becoming worse. There's a lot of people working on it. I mean, the incentive would need to come from you getting more money because you have less carcass trim, and you get more money from the packers because you have a sellable liver, right? But if it ends up costing you about $2 per head, the vaccine would need to be obviously under that. And I don't know if it was. Yep. Good question. Okay. All right. Tylosin phosphate. My suspicion, there's no real data on it. If you look at that survey, Feedlot Consulting Nutritionists from 2016, it doesn't mention Tylosin at all. Why might that be? Why might we not know the prevalence of how many people are feeding this antibiotic? Yet they don't want to report it. I don't think it's necessarily because of the VFD, but appealing to who? Yeah. There's a big call by the consumers in the US to stop antibiotic use subtherapeutic antibiotic use in the livestock industry. So no one reports it. No one talks about its prevalence and use because no one wants to draw any optics to it, right? Okay. Yep. Um, there's concern that feeding these subtherapeutic levels will lead to antimicrobial resistance of bacteria. Yeah. So if that is happening, which the data I've seen would suggest feeding Tylen is not causing AMR to happen, so antimicrobial resistance, it would be bad, right? Because we'd have more bacteria that are less resistant or more resistant to the antibiotics we're using. So it'll be less responsive. Data I've seen would suggest that we're not causing AMR, but I don't know. But there's a big call in society today to be better antibiotic stewards, right? And it's from fear of causing antimicrobial resistance. Did I answer your question? Okay. All right. So this paper, Herrick's paper again. Okay, so I think that more people are feeding tylosin in the high plains than they are in the Midwest. Okay. I think this data out of this Herrick paper would support that. So in the high plains, we're commonly going to be feeding steam flake corn, which has the highest ruminal starch availability. So we would suspect that higher ruminal starch availability will decrease ruminal pH. That decreased ruminal pH is going to cause all those other issues we just talked about and lead to an increased incidence in liver abscesses. Okay? If all was held on constant other than that grain source between these two regions. Okay? However, the high plains, okay, has a greater edible liver and lower total abscesses than these, which would be considered the Midwest. Okay. So they're at least similar to. Okay. I think that is because we are feeding more Tylen in the high plains. Okay. My perspective, I don't know this for a fact, not very many people in the Midwest are feeding tylosin. The benefit of doing so is going to be lower because they're feeding a grain that has less starch availability. That makes sense? That's my suspicion. Okay. Okay. All right. So Pacific Northwest, interestingly, had the lowest rate of edible livers and the highest incidence of total abscesses, okay, compared to the others. Okay. I think that is going to be driven by them feeding more or less corn and more of these small grain, cool season annual, like barley or wheat, okay, which will be higher, faster, more rapidly fermentable starch because they have more amylose and less amylopectin than corn. My suspicion. The other thing that's important or interesting in this paper is that coal beef, okay, so beef that's produced from coal cows, okay, still had an appreciable amount of liver abscesses, okay. So these cows are unlikely to be consuming high concentrate diets, right? So why are they having liver abscesses? Okay. Um, I don't know why they're having liver abscesses, but it could be some damage to other parts. Maybe they're uh, uh, consuming more plants that are going to cause damage or sores in their mouth and providing a site for translocation outside of the rumen. But it's not going to be because of uh, that rumen to liver transmission of bacteria. Okay. All right. Beef breeds have lower incidence than dairy cattle. Okay. Um, hmm. Already said that. Okay. So here we have coal beef, dairy cows. Okay. Then range cows have similar edible livers. Dairy cows have less total or more total abscesses than range cows. So range cows would be coal beef cows coming from grass-based systems. They have a lower incidence of liver abscesses than dairy cows. That should make sense. Dairy cows are going to be consuming more concentrate diets. However, a 16% liver abscesses, almost 17% liver abscesses from coal cows, I think is fascinating. Okay. Could be maybe we're feeding more coal cows from the beef industry, concentrate diets, right before they go off to being slaughtered. A lot of people will do this. They'll buy coal cows from cow-calf operations, put them on feed for 60 days, make their fat more from the yellow, which is associated with grain or grass, to more white, which is associated with grain. That white fat's more appealing. So you end up getting a white fat premium. So a lot of people will do that. And then maybe there's other causes of liver abscesses that we don't really understand. So I said oral or tongue as being a translocation site. Okay, so one suggestion in the West is, if these animals are consuming forbs or even get an injury caused by like a cactus or something, that would cause damage to their oral cavity, which would provide a site for translocation to the liver. 8 minutes. Okay. I think we'll have to finish this on Tuesday, but we'll give it a good college try. Okay, bloat. So ruminal fermentation yields a bunch of gas. Shouldn't be a surprise. Okay. Methane, CO2 would be the predominant ones. Okay. This gas is removed by either flow, if it's still dissolved in the liquid phase, flow from the rumen into the omasum and then down the digestive tract. It can be absorbed through the rumen wall, okay, enter the bloodstream, go to the lungs, and be respired, okay, so breathed out normally. The most of it is going to be eructated, okay. That's where rumen contraction causes the gas to be expelled through a belch, okay. So bloat occurs when this production of gas exceeds the ability of that rumen to eructate that gas or remove that gas. Bloat can cause pressure on the diaphragm, make it to where, so the rumen expanding with gas puts pressure on the diaphragm. That animal's diaphragm can't function for normal breathing, and so it causes asphyxiation and they die. Actually, in my undergrad, when I was working at the research feedlot at OSU, we had an animal with bloat. We were running it to the chute, going to give it a trocar, and it died in the snake, which was a pain. We had to break the snake apart and get a skid steer in there, and it took all day. Okay. 2 types of bloat. We have a free gas bloat, okay, less common. Then we have a frothy bloat, which is most common. Independent of if bloat's happening on pasture or in a feedlot, frothy bloat's going to be the most common. Okay. Free gas bloat's going to be usually associated with some kind of physical obstruction. So something is blocking that ruminal esophagus orifice and making it to where gas can't be expelled. Okay. Could be caused by damage to the vagus nerve, cardia, or the rumen. So that vagus nerve is what stimulates that rumen to contract. And it takes those rumen contractions to make that gas get exposed, which is at the top of the rumen. It takes ruminal contractions to make that gas get exposed to the esophagus to be eructated. Okay. Or changes in rumen epithelial that's causing the gas to get trapped. Okay. So that is less common than frothy bloat. So free gas bloat typically is caused by tissue damage. And if you have an animal that has that damage, whether to the vagus nerve, cardia, or the rumen, it's going to become a chronic issue. So you'll have animals that are just more susceptible to having that free gas bloat. Okay? Okay. So rumen hopefully this is review for you guys. It's stratified by these different layers. Okay. That gas is going to float to the top. From a physics standpoint, that should just make sense. Okay. Then classically, you have a fiber mat. Okay. So that's where the a bulk of your digesta will be stationed. As particle size gets smaller and the density of those particles increases, it will start being dissolved into the bottom part of the rumen. So fiber mat's going to have larger particle sizes. That digesta liquid phase is going to have smaller particle sizes. This ventral part of the rumen is where most of that fermentation activity is going to happen. Also, the ventral part of that rumen is where most of the rumen epithelial cells will be. And so most of your absorption is going to happen. Okay? So, rumen has to contract to get that gas cap exposed to the esophagus for eructation. Okay. I think I said all that at the top. Just making sure I didn't leave anything out. All right, frothy bloat occurs when there's a stable foam that gets formed in that gas layer. Okay. So that stable foam will trap that gas. Okay. And it will make it look like soap. Okay. And that soap, that foam trapping that gas, can't be eructated. Okay. So you can have a buildup of that gas that's being produced, and it's going to be in like a sudsy type. I don't know how else to describe it. It's going to look like soap, Dawn dish soap. Same thing happens there. That soap, as it becomes bubbly, is trapping gas. Everybody following? Okay. So, more gas gets trapped in that foam. It's going to make it difficult to eructate. So, legumes are a big source of bloat. Okay. However, that's predominantly that frothy bloat is being driven by a plant secondary compound called saponins. Okay. The sapo is Latin for soap. Okay. So saponins were named for their foaming capacity. Okay. So saponins in alfalfa, clover, other legumes are a main driver of frothy bloat from cattle grazing in legume pastures. Okay. Cool season annuals like wheat don't have an appreciable amount of saponins. I'm not going to say they have none, but it's small. Okay. Their foaming is happening because they have a high amount of soluble protein. So soluble protein is also a foaming agent. Okay. Also, through saliva and salivary mucins, so mucins are anti-foaming. Okay. So if you have diets that induce more chewing, they'll produce more mucins. Those mucins will act like a surfactant. Okay. So it's going to get rid of that foaming capacity of the soluble proteins. So these cool season pastures require much less oral processing. They require very little chewing because they're already real soft. Okay. So that's going to decrease the amount of chewing that animal has, decrease mucin production, increase frothy bloat. Okay? Hope that makes sense, because mucins will be important in frothy bloat and feedlots. Okay? Okay. Acidosis and bloat are interrelated, kind of like acidosis and all these other disorders that we talked about in a feedlot. Okay? Bouts of acidosis can cause bloat. Oh, that's time. Okay. Someone remind me we left off here on Tuesday. That's pretty good because I'm starting to run out of material for you guys. And we're going to start needing to have some guest lectures.